Hypothesis test for a population proportion. So point estimate is basically x over n, or favorable outcomes over trials. So whatever you're looking for, if we flip the coin 100 times and we got heads 40 times, your point estimate would be 0.4, which means that 0.4 of the time we will get heads. If the requirements are met, the sampling distribution of the point estimate is normal. The requirements is just the central limit theorem again, or it being a simple random sample, because the central limit theorem kicks in when it's not a simple random sample. And that's basically because kind of like the law of large numbers in terms of proportions, but in terms of population means or sample means, the law of or the central limit theorem helps balance out extremes. So we have three methods. We have the classical z-test using critical values, which basically means if the thing exceeds a number of standard deviations or is higher than a certain z-score, which is the critical point, it's unlikely. However, it being unlikely can still be a true population mean or a true population proportion. It's just highly unlikely, which is why we have the complement of the confidence interval, or the alpha. The p-value approach is the same thing as the classical approach, except we convert the z or critical value to a probability, and then the confidence interval approach should be the same thing, actually. I'm not sure what the difference is. So let's assume the proportion of people who like candy is 0.5. Let's say the alternate hypothesis is a right-tail test. It states that it is greater than 0.5. If we measure the standard deviation and calculate a z-score of someone trying to prove the alternate hypothesis and get 2.2, so it's a z-score of 2.2, or 2.2 standard deviations to the right, or 2.2 standard errors, actually, we could say, we can dismiss it, since using the empirical rule, less than 2% of data fall within that. Simply put, the classical approach is seeing if the z-score is likely, and if so, it is good evidence. P-value is the same thing, except we convert that critical value into a z-score. Here we're dealing with, we turn that critical value into a probability. And since it is, we're not dealing with t-scores, we don't have to worry about degrees of freedom, and we can just assume that the probability looks normal, that it's a bell-shaped curve, and we don't have to find the degrees of freedom that correspond. You could just find the z-score, and I'll tell you what probability is to the left of the curve. So we always use the mean equal to the null hypothesis when calculating standard deviation, since we assume the null hypothesis is true. So that's why when we do the formula mean minus the value over standard error, we always assume the mean is the true population proportion, and we see how much each point deviates from that. So we can always use the mean equal to, we already read that one. And related to the p-value approach, find your confidence interval you're comfortable with. If it falls outside, it is unlikely, but typically we'll use 95%, but the 5% is statistically significant. So if it falls outside, then that means it's rare and it's likely an unlikely value. But since there is 5% of the data that falls within that distribution, it's not automatically wrong, which is why we can't assume things, and that's the language of hypothesis testing. Binomial approach is calculating the p-values using binomial probabilities. Compare p-values to see if it is significant. So we just find the probability, see if that is likely under the area to the left of the curve, and that's it. So